We're going to look at the standard deviation, which is another measure of spread. The sample standard deviation is symbolized by the letter S, known as the Latin letter, while the symbol representing the population standard deviation is sigma, which is a Greek letter, and this is a lowercase sigma. There's no point in calculating standard deviation by hand except to get the feel of it, and that's what we're going to do right now. Later we're going to just use software. And we also want to know what this does. So what is important is that you analyze what the formula for the standard deviation is attempting to do. This is really where we're going to spend our time. Let the name of the variable be x, then say we randomly select n data values, and each one is represented by x1, x sub 2, x sub 3, x sub n. So the actual values that we select, the numbers, these are numbers. And so this right here is the sample standard deviation. Notice the sample standard deviation, so this is sample standard deviation, and this is population standard abbreviated deviation. So you see a lot of times STDev is for standard deviation. Now, which symbol for the standard deviation represents a statistic, which represents a parameter? So remember, a statistics comes from a sample. So if that's the case, the sample standard deviation, S, is a statistic, and then the population, the parameter, describes a population. So sigma here is the parameter for the population standard deviation. How often will we know this value, sigma? The answer is almost never. There's cases like chinkims of chance that we do know this value. So the whole point of sample standard deviation is to estimate. So S is an approximation to sigma. So sample standard deviation is used to estimate sigma. Population standard deviation. Okay. Now consider. Now here you can see what this equation is. If we're doing sample, notice we use x bar. If we have population standard deviation, then we need sigma. We need the actual population mean. But for a sample, we only need the sample mean. Another difference is, notice I'm dividing here by n minus 1, and here I'm dividing by n being the population size. Okay, while n here is sample size, so n is sample size. And put another mark here. Okay, so that's the sample size. Now notice that I'm subtracting from 1 here. Sorry, I'm subtracting 1 from n, and here I'm not. So why is that? That's really a long explanation, but we're going to call this, when we do this, and you'll see that we do this later, we call this degrees of freedom, and we abbreviate it by df. So df means degrees of freedom, and much later I will mention how we can view this with degrees of freedom. All right, now let's consider one term of this equation. So x1 minus x bar. In words, what does this measurement represent? And this is kind of a great question, but we're taking a difference, right? We are taking a difference between our data value, in this case x1, and the sample mean. So when we do this, what does that represent? So this represents distance between x sub 1 and sample mean, x bar. So that's what that indicates. This is a distance. So what are we really doing? And this is kind of an important calculation. We are taking the difference to find every single data values distance away from the mean. So the mean becomes the center of all the data values, and now we're seeing how far all these values are away from the mean. Okay, so how can we think of the standard deviation? Well, if you look at this, we are taking a difference, then squaring it, then adding them up, then dividing by n minus 1. So these, when we square like this is called squared differences. So the numerator has squared differences, which I know doesn't mean anything to you right now, but that's okay. So we are sort of taking an average of squared differences. Okay, so we are just taking this, again, squared differences, and we're sort of taking an average. I'm saying sort of because if I have n values, I'm not dividing by n. Here I am, notice, here I am dividing by n when I'm doing the population sample size. I'm dividing by n, but here I'm dividing by n minus 1. Okay, so it's not quite an average. But then afterwards, I take the square root. So I square, take the square root, trying to get back. So what I'm about to say next is not correct. But if you think of it this way, there's nothing wrong with it, because the thing that I'm about to say and the sample standard deviation are sort of next to each other. When one goes up, the other one goes up. When one goes down, the other one goes down. And the two numbers are not that far apart. So what I'm about to say, you can think of it, of the standard deviation, as the average distance away from the mean. So think of it that way. It's a sort of an average distance away from the mean. Now, again, using this number line, let's suppose that x bar is equal to 6. So let's say that one data value is 9. So this distance here would be 3. Let's say another value here has 2. Another data value is 2. So that distance would be 4. However, this on this side would be negative, this side would be positive. Okay. So the formula, what it's going to do is going to take those differences and square them before adding them. So in this case, I'll get 16, and in this case, I will get 9. Let's say there's another value right here, 17. How far is that away? Well, that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this one is 11 away. So that difference is 11, and I squared, and I believe that's 122. So one thing to notice is the further the data value is away from the mean, the bigger the value. So one thing that does happen is the standard deviation, say sample or population standard deviation, increases as the data variation increases, which it makes sense, because that's exactly what it's supposed to be measuring. Okay, so as S increases, as the data variation increases. So big sample standard deviations indicate a lot of variation, but you can see that it's sort of an average. Okay, so I'm about to say something else next, just to kind of catch your attention. This is supposed to be a right triangle right here. So it's a right triangle. And I'm sure you remember this connection here. How are the three sides of a right triangle connected? Well, you take one side and square it. You take the other side, this other side, literally calls that triangle, and the sum of these two equals the hypotenuse squared. But notice it is not true that A plus B equals C. That's not true. To make them equal to each other, I have to square everything. Okay, so there's a connection between these two things. Obviously, this is a triangle. This is physical, and this seems more not so physical, but there is a physical aspect to this. And this calculation is connected to this, believe it or not. As a matter of fact, the way we sample has to be in such a way that we're not altering the population makeup. It's called independence. We're going to get to that very, very end of this course, what independence means. But the independence requirement is equivalent to this being a right triangle. And believe it or not, this thing is really amazing. In physics, you would again encounter this right triangle concept. And you talk about this thing called orthogonal situations, like in vectors and such like that. So there's this formula, and what it really represents is found in many different places. Anyway, so if you look at it, I'm also squaring here and then adding them up. This is kind of a stretch here. I'm not going to try, but you can think of it maybe as there's a position and then you're finding the differences and then squaring it. Maybe that's what this is, but anyway, that's a stretch here. But again, if you want to know, in this example here, if you want to know what C is, what would you do? Let's say all I wanted to know was C, then you take the square root of both sides and you will get here, and that's what you see in this formula. Okay, I'll say one more thing. Suppose I did not take the square root of both sides and I have this s squared. So this is before taking the square root. So this would be x1, x bar squared, and so on. So this has a name. This is the sample standard deviation, but this also has a name. And what is this? This is called sample variance. And then if I did the same thing here, looked at sigma squared, this is population variance. So before we take the square root, what we do is this thing's called the variance. Is this used? Yes. But for us at the moment, no. If you looked at software output, it would give you sometimes the variance and you would see it. And one of the reasons that you would be given the variance instead of this because before you take the square root, it could be possible to use this to combine it with other things. But again, getting a little further ahead. So anyway, just remember this fact. S squared is sample variance. Sigma squared is population variance. After you take the square root, this is sample standard deviation. This is population standard deviation. All right. This is just a quick little example so we can know how to calculate this. Suppose that the number is 2, 4, 6. It's a sample for some population. Great. Let's see. Calculate the standard deviation of this set of numbers. So the first thing we want to do is find x bar. So that's what I'll do. 2 plus 4 plus 6 and divide this by 3. So 2 plus 4 is 6 plus 6 is 12. 12 divided by 3 is 4. Is that right? Did I do this right? Did this really fast. 12 divided by 3. Yes, it is. Great. Right. So now let's do this. Let's calculate this sample standard deviation. So I'm going to do this in steps. Square root of the whole thing. So I'll take 2 minus 4. First data value minus its mean squared. Then to the next for the next value, which is 4. Minus 4 squared plus 6 minus 4 squared. So I made this so I can do this in my head. And now I'll do this. Take the sample size, which is 3, so n is equal to 3, and then subtract 1 from it. So now I got 2 minus 4 is negative 2. Negative 2 squared is a 4. Plus 0, 4 minus 4 is 0. 0 squared is 0. 6 minus 4 is 2. 2 squared is 4. Here we divide by 2. And keep going. I'll have 4 plus 4 is 8. And 8 divided by 2 is 4. So before I take the square root, see this right here? This is the variance. And once I take the square root of 4 is 2. This is sample standard deviation. Okay, and then if you look at it, look, the distance from 2 to 4 is 2. The distance from 6 to 4 is 2. And you go, oh, wow, look at that. That's kind of nice. Again, I chose this specifically to make these numbers really nice. Okay. Now, and you start thinking, oh, there is it's sort of like an average away from 2. But that's not quite the case. One thing that would happen, let's say that I did not square these. Okay. If I did not square them, what would happen? So this one, notice, if I did not square, 2 minus 4 is negative 2. 4 plus 4 minus 4 is a 0. No, did I say that right? Take that back. 2 minus 4 is negative 2. 4 minus 4 is 0. 6 minus 4 is 2. But if I added these up without squaring, what would happen? I would get 0. So in fact, I would get 0 every single time. Without squaring them, I would get a 0. So one reason we're squaring is because otherwise the sum on the top would be 0. And again, I want to know how far the totality of trying to get away from the mean. You know, the bigger the difference, the more I'm away from the mean. And that's what this number is supposed to be telling me. So why not, instead of, if that's a reason that we're squaring, why not find the absolute value? Okay, so we could do 2, 0, 2. And then when I add them up, I get 4. And that actually is a calculation. It has a name. But there's a reason we don't use it. And again, I'm not going to go into it right now why it's not. Now, what would happen if I actually calculated the average distance away from the mean? Well, if I did that, what would this look like? Well, the distance here is a 2. The distance from the mean is 0. The distance from the 2, 2. So really what I have is that number. So the average distance away from the mean, in this case, would be 2 plus 0 plus 2, which is the 4. Divide that by 3. So what I would get is 4/3. And you can see that the two numbers are not that far apart. This is 1 and 1/3. This is 2. You might say, well, not that close. Okay, but if all of a sudden I changed this number and made it bigger, then this would get bigger and this would be bigger. So the two are sort of following each other. So the true average distance would be this, and the sample standard deviation would be this. And you might ask yourself, well, why not just use this? Why complicate everything by squaring? Again, it has something to do with this and something we want. And what we want is this equality to take place. And that's all I'll say right now. When we square, we're able to combine, just like I was able to combine these to figure out the hypotenuse. Well, I need to combine these distances to do something. And that's, again, why I'm squaring instead of just doing this. Okay, so there's a bigger purpose that's not seen, and that's why we decided to use the sample standard deviation instead of just this. All right, let's do this one more time. Find the standard deviation of these numbers. So again, I'm going to just calculate the average. 2 plus 4 plus 6 plus 20. So I got 4 plus 6 is 10, 12, 32. Divide that by 4, and I get 8. Okay, great. So again, I did this, so I can do this part a little faster, but eventually I'm going to get stuck. All right, so now I'm going to go 2 minus 8 in this case. So in the homework, when the samples, when these are small, you should do a couple like these, like 4 or 5. 5 is at most of what you want to do. Then after that, you're going to use software. Okay, great. Sorry, momentary doing 4. Yeah, 4 minus 8 squared. 6 minus 8 squared. And again, notice that 20 is really sort of an outlier here. Well, it's an outlier. 6 minus and 20. Should not be talking and writing at the same time. And all divided by, and again, I got n equals 4. So in this case, I'm dividing by 3, so subtract 1. So here I'm going to have 2 minus 8 is negative 6. Negative 6 squared is 64. Plus 4 minus 8 is 4. 4 squared is 16. 6 minus a here is 2. 2 squared is 4. And lastly, 20 minus 8 is 12. And 12 squared is 144. And all divided by 3. And I'll take the square root of this. So what I get here is 228 divided by 3, which gives me 76. 2028 divided by 3 equals 76. Hang on. Notice when I write my work, I try to line up the equal signs. And I also kind of expect you to do the same thing. Notice how my equal signs are all nicely lined up. It makes reading much easier if you go down. So people like to go across. It's not a good method. Going down is way better, because when you go across, and I actually messed up right here. I did not write this correctly. Again, this when you say equal, it must be equal. This better be equal to that. It wasn't there. When you go across, your eye gets interrupted. You're not sure if you should stop, and then going back and forth between the something that's over here and the beginning, it starts getting harder. But if you go vertically is much easier. Your eyes track, stop, and then you move down. And then if you want to connect, you can very quickly. So it's superior. Again, if you try to find an error and you're going all the way across, this would be horrible. Going down, your eyes are tracking properly. But I ran out of space here, and I'm going to just make a little squiggly line. So I notice I make the squiggly line to make clear that this is a separation from all this. 228 divided by 3 is 76. Right. Sample standard deviation. And again, this number, 76, is the variance. So if I want to find the standard deviation, I just need to take the square root of that, which comes out to, 8.71. 72, sorry, if I round it. So there's my variance. So you can think of this, the averages away from the mean, which was 8, is 8.72. Now, of course, this is being pulled by this outlier, this 20. So is the standard deviation a resistant measure? Remember what resistance means. Resistant means that it's not going to change much in the presence of outlier, and the answer is definitely no. So you notice 2, 4, 6, the sample standard deviation is a 2. Introduce the 20, and my sample standard deviation has jumped to 8.72. So it is not a resistant measure. So keep that in mind when you do this. So again, you can think of this as a sort of the average distance away from the mean. The mean is not resistant, so the standard deviation is not resistant.